Good morning. Carboxylic acids. I did notice that I don't actually ever give a greeting because I normally go, oh yeah, I forgot, I need to record this. And so I'm normally like in mid-sentence when I push play, which is kind of an abrupt way to start the video when you're at home, isn't it? But that's, hey, tough. Should have been here in class then. No, I'm just joking. Okay, carboxylic acids. Ready? We're going to do this and esters today. Carboxylic acid naming isn't that different from alcohols. So, in fact, actually, alcohols and esters are the hardest, so we can whip through carboxylic acids. The functional group of a carboxylic acid is your COOH. And in structural formula, it looks like this, C double bond O, OH. And it's called a carboxyl group. Okay? So your carboxyl group, that's not in the screen, hold on. Your carboxyl group is your COOH, and that's why it's called a carboxylic acid. It's not rocket science, it's the same thing. The general formula then is, do you remember the general formula for alcohols was ROH? So this is very similar. We're going to go RCOOH. Tell me if I'm going to go too fast, okay? It's made up of the OH, which is not OH minus. It's not hydroxide. However, it is called the hydroxyl group. And notice the N and YL, like a branch. Did we notice that? Okay. And this C double bond O group is called a carbonyl group. So the carbonyl group and the hydroxyl group make the carboxyl group. Okay? The hydroxyl group and the carbonyl group make the carboxyl group. Okay. We identify the the carboxylic acid in molecular formula like this. So remember how yesterday I said that you want to go, aha, it's an alcohol, right? And that's why we don't put the H with the OH in with the others. Same thing. I want to go, aha, it's a carboxylic acid. So I'm going to write RCOOH. I'm going to put that at the end because I want the reader to be able to go, red flag, I know how this reacts. I know how this is named. I know, okay. Karin, how are you writing this down at the same time? Okay. So the molecular formula for this would be, how would we write this? We want the aha. So what do we put at the end? Good. We put the COOH at the end, and the rest is just there. Okay? We do not put C2H4O2 or anything, another combination, because this does not give me an aha of any kind. In fact, this could make many different kinds of isomers. And putting my oxygen in many different places. In fact, that could technically, I'm sure I could figure out a way to make that a diol, an alcohol with two OHs. Right? So this does not give me an aha. No way, this one does. Happy? Okay, so what do you think about the boiling points of carboxylic acids? Do you think they are high or low? High. Why?
Polar.
High because they are, what's polar got to do with? No, polar has to do with solubility. So I'm not talking about solubility, I'm talking about boiling point. When I talk about boiling point, right away I think IMFs. So what kind of IMFs do carboxylic acids have? Okay, I think I heard London dispersion forces. I think I heard dipole-dipole. Hydrogen bonds. How many hydrogen bonds? 2. Do you remember us talking about 2 hydrogen bonds? Do you remember us talking about that is our new addition to the hydrogen bond family? So when we talked about hydrogen bonds in intermolecular forces in Chem 20, we said that they exist on OH, NH, and FH. And now in Chem 30, I say, yep, and there's a fourth, and the fourth is on any carbonyl group. So this, our OH, will hydrogen bond onto the OH, C double bond O, Or like that. You see that? So there's one hydrogen bond. And then here's another hydrogen bond. So you've got two hydrogen bonds here. One from the OH and the other from the C double bond O. Okay, just nod your head if you understand. Okay, so two hydrogen bonds between the molecules. One on the OH and the other on the C double bond O. Making it more higher boiling point than the alcohol of its counterpart. So ethanoic acid compared to ethanol. Ethanoic acid has two hydrogen bonds, therefore it'll have a higher boiling point. Okay? Solubility, we now talk about polarity. It's the exact same conversation that we had for alcohols. So the solubility of a short chain carboxylic acid in water is high, or very soluble. The longer the chain on the carboxylic acid, they have a long, what kind of section? Non-polar section, and therefore they're not as soluble. Remember? So C double bond O, OH, really long, non-polar end. Polar end, this is still going to be soluble, but less soluble than See that? So this will be more soluble because it has such a tiny little non-polar end, easy to dissolve. And you should know that ethanoic acid vinegar is incredibly soluble in water. Right? No problem mixing vinegar and water. Makes a really good cleaning agent, by the way, very environmentally friendly. Nod your head. Better than putting all those chemicals on your kitchen counter. Just saying. So very soluble in water. However, if I were to take like decanoic acid, not so soluble because of the non-polar end. Questions on that? Okay. So naming carboxylic acids.
Sorry, I didn't see the other side, so I was waiting till you moved. Never mind.
Copy Jordan's. Always an adventure in this classroom. Always. Okay, when we name them, we're going to take the aliphatic name. That's the alkane, alkyne, and alkane name, including that C on the C double bond O. Okay, we're going to drop the E just like we did for the alcohols, and we're going to add oic acid. Okay, so for example, how many C's have I got here? 2, and therefore it's called ethane. If it was just no OOH, drop the E and add oic acid. Have you heard of ethanoic acid before? Lots, right? Lots in our acid unit. Lots from my mouth, I would hope, by now. And it's also called acetic acid or vinegar. Okay? Yes?
What do you call it, an acid now?
Well, what's an acid by definition? Proton donor. Where's the proton it's going to donate? That one. Just like it did in the acid unit. Just like when you saw it in the acid unit, we had CH3COOH. Isn't that what that is? CH3COOH. Donate this proton and become CH3COO minus. Do you remember this? Okay. All right, so the COOH will always be at the end. So it's always given, oh, I see what I'm saying here. So this bit here always has to be at the end because this has 1, 2, 3, 4 bonds. So it can't be in the middle. It's got to be at the end. And because it's important, we're going to give this carbon 1. You know when we gave our double bond the lowest number? Same thing. We're going to give our carboxylic acid end, the carboxyl, carbon 1. So this is carbon 1, that's carbon 2. So no matter where my branch ends up, I'm still going to give this a number 1. Or no matter if that's rotated, it's still number 1. So, carbon 1. So, can you please draw butanoic acid while I scroll up and rub the board off? Yes? Can you write its molecular formula beside it? Not structural formula, molecular formula. So you cram the first bit together, and then COOH. Yes? Now, can you see that this is going to be 1, 2, 3, 4 butanoic acid? But do you know how many students look at that and call it propanoic acid? Because they just see the C3. Okay? So it's 3, 4 but. Okay, so we can use diol or triol if we need to. No, that's wrong. This isn't an alcohol. We can use dioic acid. This was a cut and paste jobby that went bad. So we can use dioic acid if needed. Is that not on your paper?
It is on ours.
It is on yours. Oh, like as in I've typed it properly on yours?
No,
No, you like cross stuff out.
Oh, I've written it and made the correction. Gosh, I'm good. Okay, so use dioic acid if needed, and if you're using your why can't I have trioic?
This is on 3 ends.
Right, has to be at the end. I don't have 3 ends. It would be a branch, possibly. I could have it hanging off of a branch, then I have to be a bit creative about my naming, but I can't have a trioic acid. You do not drop the E. Do you remember when we did our alcohols, when we did a diol, we didn't drop our E? Same thing, we're not going to drop our E here. So it's propane with an E, dioic acid. It has to do with what are they called? Vowel. It has to do with a vowel. So when we had propanoic acid, if I put the E there, it was eoic. Too many vowels. However, if it's a dioic, I don't have a vowel here, so I can leave the E on. Okay, that's what it has to do with. So, propane dioic acid has how many carbons? 1, 2, 3. Dioic acid meaning both ends have double bond OH on them, right? So, done. Happy? Karin, did you write that down?
So that would be
Well, the molecular formula for this would be HOOC CH2 COOH. The molecular formula for your I'll scroll down again so it looks like your book. There you go. Molecular formula for this would be HOOC, bit in the middle, COOH. Do you see that that's just COOH written backwards? Or Z?
But why?
For this.
But like, why does the hydrogen go first?
Because the C is bonded to the O,
Okay.
and the C is bonded to the O, and then the H. If I wrote it like this, COOH, CH2, I'm kind of implying that that H is bonded to that C, which just freaks chemists out. So the C is bonded to the C, and that's bonded to an OOH.
So that molecular formula is kind of similar to oxalic acid.
Exactly,
Yeah.
like oxalic acid. What is oxalic acid, Jordan, in your book?
HOOCCOOH.
So let's draw this then. COOH must be this. Everybody agree with that? And then this one must be COOH. And it's called in your data book oxalic acid but we could call it the IUPAC name of ethane dioic acid.
It's spelled a little bit differently in the book. Instead of a Y, it has an A.
Oh, here?
Yeah.
So, yeah, and I believe in your book it even has that in brackets, does it?
No.
No. Okay. So this is obviously the common name. This is obviously the IUPAC name. Everybody understand? We're good? Any other questions? Okay. Okay, so where do we use carboxylic acids? Everywhere. You know, what is wrong with this video? I have no idea. Anyway. Hold on. Okay, uses. Okay, carboxylic acids are used are weak acids, yes? They are weak acids, and they are present in many preservatives and foods. Preservatives, P-E-R, yes? Not preservatives, preservatives.
Oh, really?
Oh, I'm the scientist, not the linguist. Who in here is language?
I think that's right.
Per? Okay. All right, and they're responsible for their vinegar tastes sour. So, if you are bored at the supper table and you grab your jar of salad dressing, I would imagine there'll be a lot of oic acids on that ingredients list. Vinegar, oic acid. Barbecue sauce, oic acids. The longer name for citric acids is oic acid. So if you're using lemon juice or lime juice in your anythings, that's also a carboxylic acid. Okay? Pickle juice, carboxylic acid. So all of those preservatives and a whole lot of foods have vinegar in them. Why doesn't ketchup taste sour? Because of the amount of sugar that they put in it to override the sour, giving it the sweet and sour, tangy taste that ketchup provides, and barbecue sauce and everything else. Okay, so vinegar and sugar, and make your own, really is all it is. And food coloring to make it look like tomatoes. Okay, so responsible for the sour taste, citric acid, acetic acid, etc. Citric acid has 3 carboxylic acid spots on it, a branch. Okay, so normally carboxylic acids react like any other acid. So for a second here, you're going to feel like you are in the equilibrium unit, in your Kas, because that's what they are. They're acids. They're weak acids. And so, Nikita's having a bit of a freak out. 1 unit at a time. Yeah. Okay, so here we're going to donate a proton. So we're going to take ethanoic acid, CH3COOH, and sodium hydroxide, and it's a weak acid. So what kind of arrows do I need? Equilibrium arrows. And I'm going to donate a proton over here, right? And it becomes water, HOH. And ethanoic acid becomes CH3, C double bond OO minus, or ethanoate, according to the polyatomic ion table in your data booklet. And the sodium is a spectator ion. I can write them both together, make that called sodium ethanoate, or I can write them separately depending on how you fancy. It totally doesn't matter. Yeah.
Is that a double O
Where?
on the CH3COO?
CH3COOH.
Okay. And then
Ethanoic acid.
no, on the right side.
It's minus.
Here?
It's
It's
a
minus.
Oh, that's a minus sign. Oh, just
CH3COO minus.
Oh,
Just like the Ka unit.
Awesome.
Donated proton.
so it doesn't have an H at the end.
Doesn't have an H at the end. Where'd the H go? Onto here. Here's the H. In fact, I'll let me give it a color. This H and this OH became HOH. Donate a proton, accept a proton, leftover, sodium is spectator. In Science 10, you would have been able to answer that question. it just wouldn't have looked like that. You would have said, I would have said, an acid-base reaction of this, and you would have gone salt and water. Where's your water? Okay, there's your water. What's your salt? Well, it must be sodium, Na, and CH3COOH, sodium ethanoate. No H. COO minus. The H and OH means water. Okay? Harder question for Science 10, but still a question in Science 10. No different. And if this was HCl, then this becomes NaCl. Right? Cl minus. Okay. Happy? Because that was supposed to be easy. Okay, the hard one is esterification. So esterification is, well, making an ester, which I know you don't know what an ester is yet, but we'll get there. So, making an ester. So you've got a carboxylic acid from today, an alcohol from yesterday. We're going to put them together, we're going to make an ester. We're going to do it by removing water out of it. Alright, so let's draw a carboxylic acid, like ethanoic acid. CH3, C, double bond O, OH. And let's make ethanol. In fact, I'm going to put my OH at the side here just a second. OH, C. I'm going to put H2, H3. Okay? Everybody okay with writing ethanoic acid and ethanol? Hands up. Okay. I'm going to take water away. Everybody okay with that? Kind of like the polymerization unit, a little bit. So when I take water away in the polymerization unit, I'm looking for an OH and I'm looking for an H. And oddly, the OH comes off of the carboxylic acid. It's a bit weird because it's supposed to be an acid. It's supposed to just lose my H. It doesn't here. It loses the O and the H. So this is going to make my H2O. Okay, over here. Equilibrium arrows, by the way, because it's weak situation. And I end up with H, OH. Okay? Everybody with me? Now, when I do that, this poor carbon ends up with 1, 2, 3 missing something. Wants to form a new bond. Right? This oxygen ends up with 1, missing something. Wants to form a new bond. And so they find each other. Oh, isn't that beautiful? And so we end up with H3C, C double bond O, this new found bond, and O, CH2CH3. So this bit came from the alcohol, and this bit came from the carboxylic acid. And that is an ester. Yes?
How do they stay from like going back? Like when you have an ester that keeps smelling, so how do you keep it from like going back to
Le Chatier's principle. So, and actually, this is the exact example I gave when we talked about Le Chatier's principle. I had vinegar smelling, vodka smelling, equilibrium, peppermint. Right? I don't actually know if that's what it smells like, but peppermint, like artificial peppermint is an ester, and water. So if I were to remove the water, allow it to evaporate, a little bit like maybe when you spray aerosol cans, that water will evaporate, won't it? Leaving behind, allowing the equilibrium to shift to the right, Le Chatier's principle. Right? If I were to have a look at, that's about it. That's about the only thing you can really do, like, as in, like, we can do to do that. But if I'm making it, as soon as I make it, I can take it out of the situation based on density. What other things affect pressure? But these aren't gases, so this won't affect pressure. Pressure won't affect this at all. And temperature could. I need to find out if it's exothermic or endothermic. Okay? Yes.
Would lactic acid be a carboxylic?
You are not allowed to be on your computer. Focus on these sheets.
Carboxyl.
I'm not Google. You have Google in front of you, which is why you're asking about lactic acid.
Okay.
Go ahead and Google it. I'm not Google. Questions? Right. 1, 2, 3, 4. Go ahead. Draw them. Name them. And I'll do it on the board too. Steph, did you do these this morning? And did you get them right? Good job. Popoff, did you get it right? Did you remember to keep your E here?
Oh, I didn't name that one.
Can you see that this is hexanoic acid, but a lot of people are going to want to call it pentanoic acid? Don't be thrown off by that.
Longest chain.
Or that carbon does exist, yeah. Good, can I push you through? Okay, now this is going to feel a little bit like, why are we talking about this? Unit 2 stuff. But trust me, it's important. So, in terms of loss and gain, what is oxidation, what is reduction? In terms of loss and gain of electrons. Oxidation is loss of electrons, and gain of electrons is reduction. Everybody okay with that? What about in terms of loss and gain of oxygen?
Opposite.
The opposite. Are you just guessing? Okay. Do you remember why it's called reduction? A long, long time ago, where did they first come up with this name? What was reduced? No.
Isn't like
Because they didn't know it had to do with electrons. So they didn't know about oxidation numbers either. Yeah, the mass, the pile. Remember, so you dig in the ground a whole bunch of rock, and what you get out of it is a little pile of pure iron. And in the rock, what's in the rock? Iron oxides. So the size is reduced, and what happened to the oxygen? Lost, it's left. So reduction is loss of oxygen. And certainly this is Fe2 plus and this is Fe solid, and so this must have gained 2 electrons to become this way, and gain of electrons is reduction. So it fits with our definition about electrons, but it also fits with the original definition about oxygen and the pile being reduced. Draw yourself a picture if you don't remember this, because I've gone through this about 4 times now. And so oxygen is the opposite way, right? Oxidation, I mean. And so oxidation must be what? What are you getting? What are you doing with the oxygen when you go this way? You're gaining electrons. Or oxygen, I mean. Okie dokie? So, let's have a look at ethanol. Ethanol looks like this. CH3COH, CH2OH, pardon me. That's ethanol. How do we make ethanol in our parents', how do our parents make it in the garage?
Oh, through the car.
I hope not. Fermenting grapes.
But she's like in the garage.
Anna Merlot's parents own a winery, right?
Right.
Brewery. Okay, a brewery. So when they're making their beer, they harvest a bunch of wheat or hops or rye or whatever kind of beer they're making will determine on what kind of wheat combination they're using. Yes? And they put that rye in a big vat. Yes? And what does it do in that vat? Sits there and ferments. So the glucose, yesterday we talked about this, the glucose with yeast and water and warm temperatures, like 36 degrees, perfect temperature, will eventually make the alcohol, the ethanol. Right? So we've gone from sugar to ethanol. What happens if we get a little bit too much oxygen and it oxidizes even more? Yeah, we get a carboxylic acid. What carboxylic acid will we get here? What happens if I'm gaining oxygen to this guy? I'd get another oxygen on it. So I would get CH3COOH. So I've just gone from wine to vinegar.
Not so good.
Not so good. That's why they have you taste the little sampler of wine to see if it has oxidized too much and gone off. Now it's quite easy to oxidize it because you just need oxygen. And so all it had to do is that somebody tested it too often, took the lid off to test it too many times. That's all it takes. And then it's oxidized too much and it ends up being vinegar. And sometimes they do this on purpose in order to make red wine vinegar or apple cider vinegar or all those really nice vinegars that you cook with or use on salad dressings. That vinegar you wanted to go all the way. So you oxidize it. But the other ones you want to stop at only one oxidation. Does that make sense? Okay, so what is the relationship between molecular mass and carboxylic? Okay, so I think you can answer the rest of these questions on your own, keeping in mind that I'm talking about solubility there, I'm talking about boiling points here, and I'm talking about acid-base reactions for number 7. Yes?
For 4, with that diagram.
Oh, hold on. Or did the diagram I just rubbed out, you mean?
Yeah, that.
Oh, yeah, okay.
Well, it doesn't matter, but when you add the O, the
Yes.
The ethanol, does it make a gas afterwards? Does H2 form? Because where's that other H going?
A lot of other stuff forms. So in order to write that reaction properly, I would want to go to my data booklet. I'd want to look up the GERs and the LEOs, and I'd want to write 2 half reactions, balance my electrons, and get a net reaction. That's how I would do that one properly. Okay? But I'm not doing it properly. In fact, I didn't even tell you what oxidation agent I used. Could have been acidified potassium permanganate, but all I did was that. Some kind of oxidation agent. That's all. Okay? And so I haven't got the other half of the reaction. I don't have. But if I wanted to write it properly, I would jump my head into unit 2, and I would write 2 half reactions, balance the electrons, write my net. Or look at how the oxidation number has changed on that carbon. Understand if it's been acidified or not. Remember, major OH, and I would do it that way. Again, jumping my head into unit 2. Okay, so you guys have 5 minutes. I'll give you 7. 7 minutes to answer to the end of question 7, and then we'll start doing esters.